What is up, team? We're going to talk about the law of sines today. So the first chunk of this, I'm going to show you how the law is developed and like why it exists, where it comes from. That chunk is not going to be on a quiz. I think it's valuable to see it so you can like trust where it comes from and have a general understanding that it's legit versus me saying, hey, here's the thing, use it now. So hopefully it provides some value. But the first chunk of this, it's a little bit algebra heavy, and I won't ask you to recreate that for a quiz or anything like that. The second half, and I'll timestamp this in the description or something, is where I'm going to go through an example. So maybe, maybe you just want to skip to that, but I'd recommend at least checking out the algebra stuff, maybe fast forward me as I talk through this. But definitely don't worry about taking notes for the first chunk. As I get to this example, that's when you want to start writing some stuff down. Okay, so we've used trigonometry, sine, cosine, tangent, to solve right triangles, right? We've done some SOHCAHTOA stuff. What we're getting into now is like, what if you don't have a right triangle, which is the vast majority of triangles everywhere? Can we still solve those types of triangles? And the answer is generally yes. And I'm going to teach you the first rule or law that we can use. Law of cosines will be next, but we're going to focus on the law of sines today, which is a little bit simpler. So say we have a triangle like this named ABC. It's not a right triangle, but we want to figure some things out. So we're going to look at this thing in general, and there's some somewhat new terminology. We always name our vertices in capital letters. I know I always write in capitals, but capital letters are always what we use for vertices, even outside my classroom. And then we use lowercase letters for side lengths. And the way we do that is if this is vertex A, then the side that's opposite of it is lowercase a. And then the side that's opposite of B is lowercase b and c. Some letters are trickier than others because these obviously look the same. Try to make one look bigger than the other so you don't get confused yourself. Okay, so I am looking at this thing, and I'm noticing I could drop in an altitude from vertex C to the other side, making a right angle. And what this does is if I label this point D, I now have two right triangles. I have triangle ADC and I have triangle BDC. So I'm going to look at those two triangles separately and just kind of see what we can see here. So I'll name this height here. I'll just name it H. And I want to look at some sine ratios. So I'm noticing if I come at this from the perspective of angle A, if I say the sine of A, well, we know sine is opposite over hypotenuse. So the opposite leg from A, from this smaller chunk right here, is H. Whereas the hypotenuse here is B. I know that's kind of funny because hypotenuse starts with H, and here H is our height. Hopefully that's not too confusing. So again, I'm looking at this triangle ADC. I'm forgetting about this whole right side. I'm not worried about that right now. The sine of A is the ratio of the opposite leg to the hypotenuse. The sine of A, opposite leg to hypotenuse. Cool. Now, I want to solve this thing for H. So if we do just multiply both sides by B, we learn that H equals B times the sine of A. All right, cool. We're going to use that in a minute, but I'm going to put it on hold for now. Next, I now want to ignore triangle ADC and focus on triangle BDC. And I'm going to do the same thing, but from the perspective of B. So I'm going to look at the sine of B, the sine of angle B, which is the ratio of the opposite leg to the hypotenuse of this triangle here, this right triangle. So it's going to be H over A. And again, I'm going to solve this thing for H. So I'll multiply both sides by A, and then I'm going to flip-flop it again. So I get H equals A times the sine of B. Okay, here's where the fun begins. Notice that I solved both of these for H. That H is the same H for both of them. It's the height of the whole entire triangle ABC. So that means the value of this H is the same as this one. So we can create an equation that simply says B equals the sine of A. Oh, hang on, that's not even a little bit true. Hang on. So basically what I'm saying here is H equals H, which of course is true, but I'm going to take the purple H and say B times the sine of A equals the pink H, which is A times the sine of B. So we're just kind of playing some funky algebra games here. We use the ratios to get here, and then now we're just kind of manipulating things in such a way that hopefully will end up being helpful for us. So the next thing I want to do from here, let's take it up top. So I'm just going to rewrite this. B times the sine of A. And we're super close to being done with this algebra stuff. And then we'll be able to use it here in a moment. We're here. So what I want to do is I want to divide both sides by B. And I get these cancel. So the sine of A equals A times the sine of B. Boom. Now what I want to do is divide. I keep mixing them up. I want to divide both sides by A. So I'll divide, basically I'll multiply this side here by 1 over A. That's the same thing as dividing by A. The A's cancel. And I'll divide this side by A as well. So then what I find out is the sine of A divided by A equals the sine of angle B divided by side length B. That's cool. So it's neat, the relationships here. And this is what we call the law of sines. So basically what it's saying is there's 4 variables present. There's big A, big B, little b. If you have 3 of those, you can find if you have 3 of them, you can find the 4th one just by doing some algebra. Multiply both sides by whatever, throw it in your calculator, and get the missing piece. Whether it's one of the angles, one of the big letters, or one of the side lengths, small letters. And of course, this extends to C as well. So the sine of C over little c is also true. This right here is, if you didn't write down any of this stuff, that's fine. This needs to be written down. This needs to go on a cheat sheet for quiz day. Doesn't need to be memorized necessarily, but we need to be familiar with this. This is the law of sines. Sine of A equals A. Sine of B equals B, and the sine of big C equals little c. You'll rarely use all 3 of them, but you're going to pick and choose 2 of them generally to create an equation. Okay, we're going to do an example now. Let me show you how to use it, because I imagine we're confused, and that's okay. We're in a good spot. Hopefully you're able to follow where this came from. Now I'm going to show you why it's valuable. So let's look at this triangle here, ABC. And I want to find the length of A. We could also use this to find the length of C, but I want to do this for the length of A. So we're going to set up an equation here using the law of sines. Actually, before we do that, let's grab this angle measure A. We know that 85 plus 27 plus this number here equals 180. So to find the measure of angle A, we just do 180 minus 85 plus 27. And we grab a number. I didn't want to have you watch me struggle through that, so I stepped away, grabbed my calculator at 68 degrees. I'll also need my calculator for the next step, so it wasn't just for the subtraction. All right, so this is a 68-degree angle. Now we're actually going to apply the law of sines. Here's how it works. We're going to say that the sine of A, sine of 68 degrees, divided by little a, that's our unknown piece, equals the sine of B over the side length of little b here. It's opposite. The reason we didn't use C in this case is because we don't have C. So sometimes it's helpful to identify the pieces you have and the pieces that you're seeking. So in this case, if I wanted to say something like, we have big A, which is 68 degrees. We have big B, which is 85 degrees. We have big C, which is 27 degrees. Now, little a, that's the piece we don't have. This is our goal. Little b, we have that. It's 15. And then little c, this is our unknown. So we want to create an equation using 2 of these, either the a's, the b's, or the c's, where we have 3 of the 4 pieces. We have 3 of the variables. So we're definitely going to use the a's because this is our goal. This is going to be our unknown. And then we just take a peek at the b's and the c's. Well, I have both b's, so that's the one I'm going to use. I'm not going to use the c because I don't have both the big C and the little c. So we're going to set this up. I'll write it in general first. It's going to be the sine of A over little a equals the sine of big B over little b. Substituting some values in now, the sine of big A, so the sine of 68 degrees, divided by, well, we don't have this piece yet. That's our goal. And the right-hand side of the equation is the sine of the measure of angle B, big B, over the length of side length B. Now we're just going to practice our algebra skills and isolate this a. We're going to untangle this mess. So I'll just do it piece by piece. I'm going to multiply both sides by a to get this business out of here. And then we get a. Nope, we don't. Those cancel. We get the sine of 68 degrees equals a times the sine of 85 degrees over 15. A little yucky, but we can just multiply this by 15, multiply this by 15, and we end up with 15 times the sine of 68 equals a times the sine of 85 degrees. Whew, okay, we're so close. We're one step away. One more little bit of algebra here. The goal is to get a by itself. Right now we have a times a number. Let's undo that multiplication by a number and divide. So we're going to do the sine of 85 divided by the sine of 85. That's definitely how fives look. And then we see that a has the same value as 15 times the sine of 68 degrees divided by the sine of 85 degrees. Now it's a game of throwing this into your calculator. So I'll try to kind of walk through that. It's going to be hard in a video setting. We're going to be using some parentheses. So I'll say it out loud, but I don't know. Can you see the calculator? I'll try to do it like this. So I'm going to open up my parenthesis first and type in 15 times the sine of 68 degrees. And then I'm going to close my parenthesis. That closes the one for the sine ratio. Then I'm going to put a second one in there. That closes off the top of my denominator there. So I just typed in 15 times the sine of 68, and I closed it with another set of parentheses there. So I'm telling my calculator, that's the stuff in the numerator. Now, I'm going to divide that business by the sine of 85 degrees, close that parenthesis, click equals, and I get 13.96. Let's look at our picture, see if that makes sense. This is 15, this is about 14. Yeah, I'll buy that. They're in the same ballpark. If I would have got like 150 or negative number, then I would know I'm super wrong. 13.9, that seems reasonable, and for this particular example, I'm going to roll with it. So A equals 13.96, or approximately. That's a decimal approximation, of course, as all of these are going to be. Okay, let's dive into some practice problems. Please let me know if you have questions. This is tricky stuff. We're building on the stuff we've done. Now we're actually using sine. We're really just using the sine ratio here to solve triangles that are not necessarily right triangles. Super powerful tool, super clunky at first. Anticipate making mistakes, and that's okay. The more you practice, the quicker you'll get at it. Obviously, if you watched this far in the video, you've seen me make a bunch of mistakes as I went, and I kind of caught myself. So anticipate making some mistakes as you go as well. All right, you got this.